I'm Hannah Kane Latonic, and in this lecture, we will cover reverse engineering. Before we continue, I would like to take a moment to thank Mitch Adair for creating the original content of this lecture. At the end of this module, you should feel comfortable being handed a binary and examining their sections, imports, and strings. You'll know how to rename and simplify the disassembly, in addition to converting from assembly to source where needed. You'll also understand the memory layout of a process and how to figure out function arguments and local variables. Lastly, you should feel comfortable using a debugger to fill in the gaps or manipulate program execution. We're going to cover many things in this module, but we're also going to practice what we learn as we discuss each topic. Let's begin with an overview of static versus dynamic analysis, which are two general approaches for analyzing how a binary works and understanding what a binary does. Static analysis involves looking at the disassembly of a binary and is considered a safe approach for analysis because the code isn't executing on your machine. Dynamic analysis, however, involves examining the process when it is executing. The advantage to this approach is you can observe values in real time, like its registers and memory contents, and you can manipulate the process. Dynamic analysis isn't as safe as static analysis, therefore it should run in a virtual machine. When conducting static analysis, disassemblers are the types of tools you would use, like IDA-Pro and ObjDump. On the other hand, if you're doing dynamic analysis, then you'll use a debugger. On Windows, there are several debuggers available. For example, WinDebug, Immunity, and AliDebug. IDA-Pro also includes its own debugger. On Linux, GDB is a common debugger that people use. When you're conducting static analysis, you'll often utilize several common features of a disassembler, such as commenting, variable renaming, and modifying function prototypes. Within IDA, there are additional features such as coloring, grouping, and renaming nodes that can make static analysis much easier to do. When you're conducting dynamic analysis, you'll often set breakpoints or decide to step into and step over instructions. You may examine what modules have been loaded or analyze the structured exception handler chain. You may even search memory for certain contents. We're going to dive deeper into static and dynamic analysis throughout the lecture, but I wanted to give you a high-level overview so that you understand the difference between static and dynamic analysis, as well as the general approach taken between the two. Now, let's jump into PE and ELF. Windows binaries and DLLs have a portable executable file format, or PE for short. In fact, only one bit separates an executable from a DLL. On Linux, Unix, and Apple OS, its executables and shared libraries have an executable and linkable format, or ELF for short. Here are some images depicting an ELF and PE file format. The key takeaways from this slide is that each format has a collection of fields, and each field will have a particular meaning which is represented by a certain value. The file formats also have sections, which is generally a logical collection of code or data. Each section will have its own set of permissions like read, write, or execute, and will have a name associated with that section, like .text or .bss, for example. Permissions are important to be aware of, especially when you want to exploit a binary, say to obtain the flag from a capture the flag binary. If you want to write your shellcode somewhere, you need to write it to a viable section. Furthermore, if you want to execute your code or redirect control flow, the section has to be executable. Okay, so why is this useful? By initially looking at this information on the surface, you can quickly get some insight into what the binary is doing. For example, you can learn what libraries it loads. Say your binary is importing socket libraries, then the binary likely handles network communications. You can then verify this by looking at what functions the binary uses from its imported libraries, such as send and receive. Looking at its imported libraries and its corresponding functions are quite useful for identifying vulnerabilities. You can also determine if the binary is packed or not. Indicators of this include weird section names or sizes, lack of strings, and lack of imports. When analyzing executables with a PE format, you can determine all this information in tools like CFF Explorer, IDA Pro, and PE File, which is a Python library. For ELF binaries, you can research this information using readelf, objdump, and file. Here's an example of CFF Explorer, where we are examining the section headers of calc.exe. Each section has a name, virtual size, virtual address, and so on. The characteristics column represents the permissions of the section, specifically if it's read, write, and execute permissions. Here's what a packed or a compressed executable looks like in CFF Explorer. You can see that the executable is packed with UPX. On Linux, you can get the same information using the -s option of readelf. For example, running readelf on an arbitrary binary, the output shows you the names of each section and their respective permissions. And the respective permissions are demonstrated under the flag column. To look at the imports of a binary, you can open it in IDA, for example, and click on the Import tab. In this image, we're showing you what string libraries are imported. This is useful if you want to identify if the binary is using any vulnerable string functions. Next, you may identify what strings are used by the binary. Here, we're showing the string output in IDA from a recent CTF problem. You may notice the get your flag string. It would be advantageous to start your analysis there and work backwards, allowing you to focus on what components of the binary you actually need to understand in order to obtain your flag. Let's jump into an exercise to practice what we've learned. Open numberchecker.exe and numbercheckerpacked.exe. Compare these two. For example, look at their imported libraries and note the difference. In CFF Explorer, look at different fields in the PE format, look at the sections, and just feel free to explore the information that CFF Explorer presents you. In IDA, check out the strings and imports along with exploring the sections of the binary. Let's now discuss the topic of assembly. There are two syntax options, AT&T and Intel. AT&T syntax is dominant in Unix environments since Unix was created at AT&T Bell Labs. The parameter order after the instruction is source, then destination. For example, move EAX into EDX. Intel syntax, originally used for documentation of the x86 platform, is dominant in MS-DOS and Windows. The parameter order is reversed. For example, move to EDX from EAX. Many x86 assemblers use Intel syntax and is more commonly used, so we'll use this syntax for the rest of the lecture. Here, we have two similar instructions, but you'll notice the second instruction uses brackets while the first one does not. The first instruction will move to EAX the contents from ECX. The second instruction will move to EAX the contents of what ECX is pointing to. In this case, ECX is a pointer. To move its contents into EAX, it must first be dereferenced, which is what the brackets represent. In C, this is equivalent to pointer dereference, where EAX equals the dereference of ECX, represented by the asterisk. In addition to registers, you can also use memory values and its immediates. For example, move into EAX the value 5. In our second example, we're moving into EDX what this address at 1, 2, 3, 4, 5, 6, 7, 8 in hex points to. There are a handful of common instructions to be familiar with and to focus on when analyzing a binary statically that will help give you a big picture understanding of what the binary is doing. For example, the call instruction will call the function located at the address 1, 2, 3, 4, 5, 6, 7, 8 in hex. Next, we have compare EAX to the value 8. Notice how the comparison is conducted left to right. Typically, a jump instruction will occur when a comparison is made. The first jump instruction is an unconditional jump, where you will jump to execute the instruction at address 1, 2, 3, 4, 5, 6, 7, 8 in hex. And again, this just represents an arbitrary address. The JLE instruction represents a conditional jump, where you will jump to the address if EAX is less than or equal to the value 8. The JG instruction indicates that you will jump to the address if EAX is greater than the value 8. A comparison instruction is simply a subtraction operation between the two operands. The appropriate jump instruction will be used if the condition or result is unsigned or signed. Let's step through this example to get an understanding of what this program does by practicing what we learned. Let's focus on the instructions we know, which are move, compare, jump, and call. We're going to ignore the first three instructions, which represents the prologue, but we'll describe that more in detail later. We'll start with the instructions in the highlighted box. We have a move instruction where EBP-4 is first dereferenced, and what it is pointing to is now assigned the value 4. For the second move instruction, EBP-8 is dereferenced, and what it is pointing to is now assigned the value 10 in decimal or hex A. Then we move to EAX the value pointed to by EBP-4. On the left, you'll see the pseudocode representation of these operations, and we know that register EAX is containing the value 4. Now, we encounter a compare instruction, where we are comparing the value of EAX to the value pointed to by EBP-8. That is, we're comparing the value 4 to the value 10. If the value 4 was greater than the value 10, we would jump to the address 80483D7. Since this is false, execution will then continue to the next instruction. The next instruction we execute is moving to EAX the value of 1. Then we execute an unconditional jump to 80483DC. This means we're jumping over the move instruction to the leave instruction. Then we return from the function. Right now, we're focused on the instructions we've covered, so at this time, don't worry about what the leave and return instructions do. Let's recap what this function does. Two memory addresses relative to the pointer contained in EBP were assigned the values 4 and 10. A comparison occurred, and if the first operand was greater than or equal to the second operand, then we jumped to a particular instruction. If not, we continued executing the next instruction. Register EAX was assigned the value of 1, and then the function returned. We have a high-level understanding of what is going on, but let's dig deeper into the details. For example, what does dword pointer mean? For example, you may have noticed it preceding the dereference of EBP -4. Dword indicates the size, while pointer means to dereference the value accompanied by the brackets. However, in some cases, the size of a referred to memory region is ambiguous. The assembler must be explicitly directed as to which is correct. The size directives byte pointer, word pointer, and dword pointer serve this purpose, indicating sizes of 1, 2, and 4 bytes respectively. Each of these byte sizes represent a data type, such as a character, short, or integer. Since a dword is 4 bytes, we now know that EBP -4 is pointing to an integer. So we dereference EBP -4 and move the 32-bit integer representation of the value 4 into the 4 bytes starting at that address. We can hypothesize that the source code likely has a variable hard-coded with the value 4. Now we have a better understanding of these two move instructions. In C, this may look like int x equals 4 and int y equals 10. But are these local, global, or static variables? This will require us to explore the topic of process memory layout to answer this question. Before doing that, let's recap what we've learned so far. We have two variables that are assigned the values 4 and 10 respectively. If 4 is greater than or equal to 10, we jump to the address at main plus the offset of 23 hex. Else, EAX is assigned the value of 1. We then jump to the address main plus 28 in hex and return. Now that we have pseudocode to work with, the disassembly doesn't look that scary and mysterious anymore. By discussing process memory layout, we'll be able to address the existing knowledge gaps about our program example, such as why are things relative to ESP and EBP? What are the push and pop instructions doing? And what is the purpose of the leave and ret instructions? For reference, here is the process memory layout for Windows, which you can get further additional information at the link provided at the bottom right of this slide. And here is the process memory layout of Linux, which you can research further at the link provided in the bottom right-hand corner. These two slides are provided for completeness, but we're going to dive into these memory layouts in a later lecture. What I do want to cover is the layout of virtual memory. Every process has its own virtual memory to work with, and this is what the process looks like in memory. This is a simplified memory layout of the previous two slides. Regardless if your process is running in Linux or on Windows, it has 5 main memory sections, and they are text, data, BSS, heap, and stack. The text section contains your machine instructions, and this section is usually readable and executable. The data section contains your initialized global and static variables. Say, for example, int x was defined as a global variable and initialized to 4. It would then exist in the data section. However, if int x was declared as a global variable and not initialized, then it would reside in the BSS section. Your stack will contain your local variables and is utilized to pass arguments to functions. Lastly, the heap is used for dynamic space. For example, when you dynamically allocate memory using malloc, it will reside in the heap. Let's talk briefly about registers. Here are the 9 general-purpose registers of an x86 platform. EIP is your instruction pointer. It indicates what instruction to execute next. This is what you usually look to control when you want to hijack a program to exploit it. EAX typically will hold the return value of a function, which in our example, EAX was assigned a 0 or 1 right before the function returned. The other 2 registers I want to highlight are ESP and EBP, which are your stack and base pointers respectively. They point to the top and bottom of your stack frame, which every function has. Let's talk about the stack a bit more. Your stack frame grows from high to low memory addresses. The stack frame is populated and modified by pushing values onto it or popping values off of it. Therefore, it's a last in, first out data structure. ESP points to the top of your stack, while EBP points to the base of the stack. When you see EBP minus an offset, say EBP minus 4, in our program example, then it is referencing the function's local variables. On the other hand, when you see EBP plus an offset, you are accessing the function's arguments. When a subroutine is done, it adjusts the ESP and EBP pointers accordingly so that when it returns, then the pointers are in the correct position for the parent function. We covered briefly the registers, stack, and process layout. Let's apply what we just learned to determine the stack layout of our program example. Originally, we ignored the first 3 instructions. Now, let's explore the third instruction, where we subtract 10 hex or 16 decimal from ESP. Remember, the stack frame grows from high to low addresses, so ESP will move towards a lower address by that amount. The purpose of this is to make room for the function's local variables. The move instructions containing EBP minus 4 and EBP minus 8 involve local variables because we are accessing the variable at a negative offset of EBP. Also, we now know that the return value stored in EAX is either 1 or 0 depending on the comparison. Let's illustrate the stack frame of our program example given what we know. ESP is pointing at the top of our stack frame. We have our 2 local variables at EBP minus 8 and EBP minus 4. We have our base pointer followed by the function's return address. That is, when the function is done, the program knows what address it should return to. Lastly, if our program had arguments, it would begin at an offset of EBP plus 8. Since our disassembly does not show an instruction involving the dereference of EBP plus an offset, the function is not using any of its arguments, if it has any. Let's add this knowledge to our pseudocode. We have some function that is returning an integer of value 0 or 1. We have our 2 local variables defined and assigned the value 4 and 10 respectively. If 4 is greater than or equal to 10, we will jump to a particular address where EAX will be assigned 0. Else, we will assign EAX the value of 1 and jump to another address to return from the function. One thing to keep in mind is that if comparisons get translated in an opposite fashion when going from source to assembly. For example, the condition if x is greater than y in your source code becomes the following assembly instructions. Compare xy and then jump to an arbitrary address if the value is less than or equal to. In assembly, we're actually testing if the condition is not true. If it is false, then we jump over it. Take the condition if x is less than or equal to y. It becomes compare xy and then jump to an arbitrary address if the value is above. So when you see jump above, the developer actually wrote less than or equal to in their source code. Given this insight, we can now update our code. Before, we noted the condition as if 4 is greater than or equal to 10. But since the source code should reflect the opposite of the jump instruction, we change it to if 4 is less than 10. Since the jump is not taken because 4 is less than 10, we will return 1. Otherwise, we return 0. Now we have our completed source code for our program. We've covered a lot so far, but here's an exercise for you to practice on your own. Produce the source code for the following function. Determine how many local variables exist, how many arguments there are, and their types. We haven't covered one instruction in this exercise, which is LEA. But as a hint, consider it the same as EAX equals EDX plus EAX. Pause here and try the exercise. On the next slide, we will present the solution. The exercise was a sum function. The function takes two integer arguments and returns the sum of the two. The LEA instruction was simply used for efficiency by the compiler. EAX contains the return value, and you may have noticed in the disassembly that the function does not have any local variables. Now, let's dive into functions. The previous exercise leads us into exploring how function calls are handled. We know EAX holds the return value and arguments begin at EBP plus 8. But how exactly are the arguments handled? There are two main calling conventions that are commonly used. The first is cdecl. This originated from C, and the arguments are pushed on the stack in the order of right to left. The thing to remember about cdecl is that the calling function cleans up the stack. The second calling convention is the standard call. It originated from Microsoft and also pushes its arguments onto the stack from right to left. The distinguishing feature about this calling convention is that the called function cleans up the stack. Therefore, it must know how many bytes to clean up ahead of time. Here's an example of the main function that later calls our sum function. Note that GCC prefers to move arguments onto the stack, whereas Visual Studio will usually use the push instruction. Either way, the arguments are placed on the stack in order of right to left. Since we have our arguments 5 and 7, the value 7 is assigned to the dereference value of ESP plus 4, and the value 5 is assigned to the dereference value of ESP. Here's what the stack frame looks like before it makes the call to sum. We have our return address and EBP pushed on. We adjust ESP to make room for two local variables. We then move the value 7 onto the stack, followed by the value 5. Now the stack frame is ready to make the call to sum. Functions reference local variables and arguments via their stack frame pointers ESP and EBP. So every function has its own prologue and epilogue to adjust ESP and EBP accordingly so that they are pointing to the correct content. The prologue will consist of pushing EBP to save it on the stack, then moving EBP to the top of the stack, and finally making room for local variables. The epilogue involves moving ESP back to EBP, popping the top of the stack into EBP, and then returning to the address on top of the stack. The epilogue may simply involve a leave instruction, which is equivalent to move ESP, EBP, and then pop EBP. Now let's explore what happens to the stack frame when we call sum from the main function. We first push on the return address. We save EBP by pushing it onto the stack. Now we assign ESP to EBP, so they're both pointing to the top of the stack. We move the argument at EBP plus 12 into EAX, so EAX now equals 7. We then move the argument at EBP plus 8 into EDX, so EDX now equals 5. The LEA instruction copies the address of the expression EDX plus EAX times 1 dereferenced into the EAX register. Since the effective address is the resulting sum of these two registers, this instruction copies the value 12 into the EAX register. The function needs to clean up now. So we pop EBP, setting EBP back to the caller's value, and now we return by popping the return value into EIP. When exploiting a binary, if you can control the stack in any way, it's possible to overwrite the return address so that when it's popped into EIP, it will then execute your code instead of the original program. The control flow returns to the next instruction in the caller function, in this case the next instruction of our main function. Here's another exercise for you to practice on your own. What is the stack going to look like at the printf call? Start in main and work through the program up to the printf call. Pause here to work on this exercise. When you're ready to check your answer, resume to find the solution described on the next slide. When executing the main function, the return address and EBP are placed on the stack. When we go to call function 1, we push the arguments on right to left, so we first push on Sally and then the value 29. We also push on the return address. When we enter into function 1, we push on our saved EBP. We push on our local variable real age, and when we encounter the call to printf, its arguments get pushed on, again from right to left. So we push on real age, followed by name, and finally we push on our string represented by a character pointer.